version and some more other requirements. Here's a sample of a simple Docker file taken from several years ago from CentOS project. And you can see that it's, while being perfectly usable for development use, it's pretty bad for actual redistribution. And people don't really rely on those kind of images produced by those simple Docker files. First of all, it installs the MongoDB server, but it doesn't give you any clue what kind of a version is that. Is it MongoDB 2 or 3, or even an exact RPM version of the MongoDB? It also produces a single layer for each instruction, which gives you literally 7 layers for just one part. That might be useful for development again, but definitely not usable if you're redistributing an image with a MongoDB. It also is pretty shady because it creates directory data.db, but doesn't explain what is that. Is it a volume? Is it a temporary directory? What's it used for? And this Docker file also doesn't give you any hints about how to customize it or to use a config. So the way to add this missing information is actually properly labeling it. There are several projects which are aimed to standardize the set of labels, and they are supposed to provide you with the necessary information about what's that. So the difference is the actual data label layer, which installs all of the RPMs and all of the stuff, is now condensed in one, right here. The next label, called BZ component, is giving you which component should you file bugs against if you find some. It also explains which version is it installing and exact release of this container image, because without changing the RPM exact version of the RPM, you may change some more details in this particular container image, and you might track this release as well. It also gives you a help message about what MongoDB is, and it also standardizes the run label for how to actually use this image, which Docker run parameters does it expect, and it's perfectly usable with the Atomic CLI program, so it can install a systemd service and start the MongoDB service automatically. This image will also create, again, a bunch of layers, which are barely useful when this image is being distributed. So what we need to do is to squash them into one. And for this particular task, we might need a CLI task called Docker Squash. We also want to give additional tags to the images, because customers might want to stick to the latest version, to the latest version of Mongo 3.2, to a particular version, and we might want to produce some scratch builds for developers. And for those scratch builds, we want to give them some random label, which is, in our case, is a timestamp. So there is pretty much a lot of work for making a redistributable image. And we have invested a lot of time in automating this process. The result of this was a Python application called Atomic Reactor. What it does is it's a set of plugins which we might want to enable in order to produce an image. For instance, we always want to squash them. We always want to tag them with the latest version. In some cases, we might want to add an additional Yum repo and install the packages from there. In some cases, it's not. So the Atomic Reactor takes care of that. It's available on GitHub. We're installing it with pip. And the first thing Atomic Reactor needs, it obviously uses container itself, and we're building this in a container too. And what you need is a thing called build.root. It's a container with all of the tools enabled, packed in one, and we would be using it to produce another images. So first of all, we're specifying the Docker image for our build.root, and using command create build.root image, we're creating a build.root. Later on, we're building a MongoDB using that image, picking up the base package from this repository, and using this Git repo for the Docker file. The whole configuration of Atomic Reactor is stored in JSONs, and this JSON file specifies what are the source parameters of our image, which plugins do we want to run before the build. For instance, we always want to pull the fresh base image in order to make sure that the previous one on the build node is not cached. And after the build, we want to tag and push it to another registry. And that's probably all the actions we want at this point. Inside the Atomic Reactor, what happens is it's parsing the build JSON, makes sure enables the necessary plugins, executes them, and finishes basically the build. If we have a prepared build JSON, we can specify it in the CLI. There is a bunch of Atomic Reactor plugins in that repo. The most useful ones are, for instance, for most Docker files, we don't want to specify from Fedora 27. We want a specific manifest digest, which was used for this build. So in the Docker file, which we take, we also replace the from line with a from line specifying the exact manifest which was used for this build. We also add the necessary labels, additional ones for tracking, for instance, the VCF ref, which is the commit hash of which was used to build this plugin, and so on and so forth. For the builds, we're also embedding the Docker file which was used to produce this image inside the image itself. So we're adding additional instructions and then squashing it. Atomic Reactor is able to convert the help file from the markdown into the man-compatible format. So using the Atomic CLI help, it's able to display you the help for this image. Some projects are requiring additional YAM repos, so we can specify the necessary YAM repo for when we're building a new image. Those are the images which are happening before the actual Docker build is happening. There is a bunch of other plugins which are post-build. That's the part which happens after the image is built. We want to do some operations for it. We'll, for instance, squash all of the layers into one. After that, we can also tag it by layers and actually push it to the registries. We're also making a list of all of the RPMs which are into this image. Atomic Reactor works on one particular machine, and it simply doesn't scale. In order to produce a bunch of images, we need to make sure that all of the requests are scaled across several ones. And in order to scale, we're using OpenShift for that. And Atomic Reactor works with a tool called OSBS client, which scales the requests to build containers across the whole OpenShift. In order to display what's the current state and display the information about the built images, OSBS client is also integrated into Koji, so it looks just like an average RPM build, if somebody's familiar. It's very similar. Instead of, for instance, flatpak build, we're using flatpak container build. For the developers, it looks exactly like that. Instead of build, we're using container build. This request is sent to Koji. Koji is sending the request to OpenShift to start the build. The OpenShift picks a node which will do this particular image build, starts the container with the build root, passes the build JSON to atomic reactor. The build happens and is being pushed to the registry. In the end, on the CLI, you get a link to the Koji build and the pull specs for all of the images created, depending on which tags were used. That case happens for the one particular architecture because OpenShift cannot mix different architectures under one cluster. As a result, we've created an orchestration scheme which makes one of the OpenShift clusters be the orchestrator. It's passing requests to different clusters which are running under different architectures, and in the end assembles them using the fat manifest, so-called, in the Docker. So it creates a fake manifest which is pointing to different images depending on which architecture is requesting this image. For the rebuilds, we're using several OpenShift features which are build configs and image streams. And whenever the base image for a particular image is being updated, we're able to rebuild the whole chain of images which are depending on it. This is leveraging the OpenShift's image stream functionality, which is able to trigger additional builds. In the end, Atomic Reactor is also able to create a build back in Koji, although there has been no Koji task which has triggered it. In order to make a shortcut for instance, for CVE builds, we might first want to build the end-user containers first because it's very urgent to build them first. We're using an isolated build feature, which is able to build the very same package, just repeating the whole procedure, but pointing to a different YUM repo, which has the fixed, fixed YUM packages. Now for the demo. For the demo, I will be showing how one of the tools we're using for development, it's called OSBS Box. It's a set of containers which is starting OpenShift, running Koji and the registry, so you can have a self-contained builder on your machine. And we're going to build the most important CLI package of all time. It's Kausei. Here's the Docker file I'm going to build. It simply specifies that I want a Kausei from Fedora 27, specifying the label for my package, the version, and the component which should be used for the bugs. In this image, I'm going to install the Kausei, clean up the cache, and define an entry point. After that, I'm going to start a new container build, specifying that I want to have it tagged with a candidate tag, take the Docker file from this GitHub, and use the branch Kausei. Meanwhile, on my local Koji, we're going to see a new task has been created. It's in the progress. And the logs say that, first of all, let's not be that fast. First of all, Atomic Reactor is checking if the Docker file is valid. It checks that it has necessary repos. It explicitly also lists all of the environment variables here, verifies that automatic labels are correct. For instance, here we set an automatic label called build date, specify the architecture, and we're outputting the Docker file which would actually be used for the build. The difference is that from line has been replaced to signify not just any Fedora 27, whatever this stack is pointing at the moment. It's specifying the exact manifest digest used for this file, so we can repeat the build at any time. In the end, this image will also include the Docker file which I used to build, and a bunch of additional labels. The actual build is progressing. At this point, we're also running a Squash plugin. So my image will have only Fedora layer and additional layer which with all of the information I have specified. To cut this thing short, well, it's going to take some more minutes, and we only have 5. In the end, eventually it's going to push it to my... Oh, okay, squashing is eating all of my I/O. Great. Nevertheless, while it's progressing, we can move on to the questions. Okay, I'm going to skip it next time. Any questions?
Can I run the atomic reactor locally without the set of containers running on the ground?
Definitely. It's a Python CLI application. Again, you either need a formatted Docker file or a build.json with additional plugins, but it's certainly possible.
As I understand, atomic reactor is a worker, which feels like just one image, and the OSBS is an orchestrator which runs atomic reactors with multiple, big numbers. Are there plans to make OSBS a generic tool to build containers rather than a tool which is connected with OpenShift and Koji right now?
So the question is atomic reactor a worker? Yes. Is OSBS being an orchestrator or some kind of a wrapper? Yes. Are there any plans to make all of this into one piece? No, it doesn't really make... The point is not just to run Docker build on your local machine and to have all of this in one CLI. The point is to have it distributed, scaled at this time. There is no... different parts are running in different stuff. For instance, in Koji Builder, one part of Atomic Reactor of OSBS client is redirecting requests from Koji to OpenShift. That's all it does. Another part is creating a build config in OpenShift. And the other part is taking the build.json and building. There is, if I understood correctly, you want this into one?
Not exactly. My question was if we can untie OSBS from OpenShift and Koji and use it as a generic view system. So Atomic Reactor is one piece, but OSBS currently, as I understood, is it's using Koji and OpenShift extensively, and it's not a generic.
You certainly can tie away from Koji if you write your own setting for instance, OBS. In the end goal is to make Atomic Reactor with a build.json running in container and whatever. Any ways which lead to that are great, and Atomic Reactor doesn't enforce you. It has a set of plugins which send information back to Koji. It can as well have a set of plugins which send information back to OBS, to anything else. Oh, great, build finished. And we're certainly going to make the cow say the words. After the build is finished, we get a link to the Koji builds produced by that. Those are architecture specific, so we can list several builds. And the actual pull manifests for all of the images produced. For the future plans, the team is working hard to make sure that after the build, the containers can also be signed. So we would make sure that with every pull manifest, we also get the whole container signed with GPG, and we can verify that that container we have pulled is actually produced by Red Hat, but not by some random stranger. And another move is to go away from Docker daemon to move completely into OCI tooling, which will help us to produce the OCI-compatible images without using Docker. If you're interested in all of the topic, there would be several related talks related to OSBS, Atomic Reactor. That would be Owen Taylor's distribution of flatpaks on the distribution level. The guys are using several parts from OSBS and producing OCI compatible flatpaks. Fedora people, for instance, Patrick Uderwijk would be speaking about how they are approaching the whole rebuilds problem, which happens when the base image is being updated. They have a slightly different solution, but also pretty interesting and exciting. So, any other questions? Sure.
Hi. Is Reactor able to help with building the same container later in time? Like, if you build the container with some RPM packages, it depends on the exact point in time and the state of the repos. If you want to rebuild it later and use exactly the same packages, that's a problem. And there is no to use something like a time-specific shift in time in repositories or something like this.
Can it reproduce, the question was, can Atomic Reactor rebuild the very same image with the very same RPMs built with that? No, but it's a good feature. We have the links to the very same repos. At the end of the build, we're also collecting a list of RPMs which were used during the build, so that's definitely possible. I have never seen the need for that, but that's sounds like it requires an additional plugin, but yeah, it's possible unless the repo is completely different, or for instance, there would be packages. So no, but definitely possible. Sure.
What about populating the version automatically? You kind of mentioned that would be good to automate, but is that something that's actually on the roadmap?
It used to be on the roadmap, but it's not that easy because you can build packages not just from RPMs, but also from jars, from middleware, and from anything. And some components don't follow that scheme of having one same version across all of the components at once. It would work in 99% of cases, but that 1% of case would be completely different. At the moment, you have to specify it yourself, and it's more like a signature that you understand what you're doing. It would be nice to do automatic stuff, but it's just not that easy in the real world, unfortunately. Good. So thank you for your attention.
So please don't forget to rate the talk at the DEF CON webpage. Lunch, so the faculty canteen is open, so feel free to grab the lunch. It's right across the street, first floor. And with the network load, if not necessary, please consider disconnecting.